Good morning, all. Hello, am I audible?
Yes, sir. Good afternoon.
Good afternoon, all. Myself, Tilak Pandya, PhD Research Scholar at Department of Physics, Saurashtra University, Rajkot, welcomes you all on this platform named Vigyan Yatra, a travel for scientific Indian minds toward the Vikshit Bharat. Vigyan Yatra is a series of conferences session from March 4 to 15, 2024, and is jointly organized by the Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati VIBHA, GUJCOST, and Department of Science and Technology under the Gujarat Vigyan Sammelan 2024. We are honored to have with us Dr. Tejas Patalia, Principal of VVP Engineering College, Rajkot. We are extremely grateful to our patrons and co-patrons, Professor Nilambari Dave, Honorable Vice Chancellor of Saurashtra University, Professor Chaitanya Joshi, President, Vigyan Gurjari, Gujarat Prant, Professor Girish Bhimani, Dean, Faculty of Science, Saurashtra University, Professor Narottam Sahu, Honorable Advisor and Member Secretary at GUJCOST, Gandhinagar, Dr. R.G. Parmar, Registrar, Saurashtra University. I heartily welcome our today's invited speakers, Dr. Vaibhav Kulshrestha, Principal Scientist CSIR, Central Salt and Marine Chemical Research Institute, Bhavnagar, Dr. Shubhadip Neogi, Principal Scientist CSIR, Central Salt and Marine Chemical Research Institute, Bhavnagar. I also welcome Professor Nikesh Shah, Professor and Head of Department of Physics, Saurashtra University, Professor P.N. Joshi, Secretary, Vigyan Gurjari, Saurashtra Prant, Rajkot, Professor Mihir Joshi, former Professor and Head of Department of Physics, Saurashtra University, Dr. Piyush Solanki, Assistant Professor at Department of Physics, Saurashtra University, Dr. David Dhruv Sir, Assistant Professor at Department of Physics, Saurashtra University. Moving ahead, I request Dr. David Dhruv Sir to welcome and introduce us to today's guest. Dr. David Dhruv Sir is Assistant Professor at Department of Physics, Saurashtra University, and coordinator of this event, Vigyan Yatra. Over to you, sir.
Thank you very much, Tilak Pandya, for the introductions and your kind words about the Vigyan Yatra. Now, on the somewhat we can are going to on the this acceleration process of Vigyan Yatra, and then after by listening the all the invited speaker, today we are going to conclude the somewhat this event in the next stage. So I'm most welcome as well as I'm warmly welcome to the our today's guest, the Dr. Tejas Patalia sir. Before giving his introductions, I am very much enthusiastic to just share that the somewhat I also work with him and I find out the lot of courage and the lot of the knowledge from the Patalia sir, and always he is motivated students for the develop their inbuilt skills towards the developing the engineering field, and although that will be definitely helps to develop the nations. So although the Dr. Tejas Patalia sir is currently served his duty as a head of department as well as a principal of VVP Engineering College, which is a very established engineering college in Rajkot region. He is also life member of IST. He has completed his BE from the computer engineering from the South Gujarat University. He had completed his ME Masters from the SP University, and he holds PhD degree from the computer science and engineering field. He has published more than 26 research articles in the very reputed national international reputed journals, and he has guided more than 100 undergraduate students through their project systems in a fourth semester or fourth year. Rather than that, the 10 post-graduation students have also been guided by the Dr. Tejas Patalia sir, and he possesses a technical experience more than 18 years for the UG students as well as the 6 years of PG levels. And he always says and he always talking about the development or better development of the students by the activity. He believe in activity and he always give the students so many activities and enthusiast students to give that activities. So I warmly welcome to our guest Dr. Tejas Patalia sir.
Yeah, thank you very much, David sir, for the introduction. Uh, First of all, very good afternoon to all the dignitaries and the participants, those who are present under Vigyan Yatra and Gujarat Vigyan Sammelan. So today's series of conference is mainly, our tagline is a travel for scientific Indian minds towards Vikshit Bharat. So under this title, today we are also having two experts, scientists, Dr. VIBHA and Dr. Suhadip sir, who will give a brief idea about the series. Currently, as I am from computer engineering background, so I would like to share and highlight few points with respect to my background. That is, nowadays, due to the research areas which are explored widely, we are having different types of technologies available in the market. Due to this type of events, like Vigyan Yatra and under that Gujarat Vigyan Sammelan, we can explore many areas widely. For example, let me tell you that our government nowadays is aggressively focusing on artificial intelligence. And we all know that what is artificial intelligence and how it works. Artificial intelligence has captured almost all the sectors of the industries nowadays. Like we can say automobile industry, chemical industry, electrical and mechanical industry, or civil industry. Any sector you take, nowadays artificial intelligence is growing wider and wider, and we all are coming in touch with such type of technology. And as I said, that government is very aggressive in such type of areas. Government is also funding different types of startups in artificial intelligence. Currently, government has announced India AI mission, India AI mission, in which last week only the Union Cabinet has announced or approved rupees 10,371 crore of investment for only artificial intelligence mission. So we can think that how this particular revolution will going to take place in our day-to-day life. So this mission, that is India AI mission, this mission aims to establish a very comprehensive ecosystem and to promote different types of AI applications in various sectors. Ultimately, we can say that it will align to the vision of like Make in India, or we can also say Make AI in India. We are day to day we are getting strengthened in software industry. So at presently, we all know that in foreign countries also, our Indians are majorly involved in software development. So the mind is available with all our Indians. So due to such type of initiative by government, the prospects of future for the young scientists, young science students, engineers will be very, very bright. So we are growing on the software side. Parallelly, also we are growing on in the hardware side also, because the technology is a combination of hardware and software that we all know. Now on hardware side also, government is initiating very much. Recently, the government has it came into the news, if you have heard, that our Prime Minister Narendra Modi ji has announced the foundation stone of 3 semiconductor plants. So these 3 semiconductor plants will be implemented in Dholera, in Assam, and in Saran. So due to this particular 3 semiconductor plants, all type of different hardware components will be manufactured in our country only. Approximately rupees 1.25 lakh crore will be invested in semiconductor industry, and it is a part of Make in India process. So ultimately, such type of initiative will take our country from developing to developed one till 2047 as a Vikshit Bharat. And currently, we all are using laptops, desktops, computer system, and we all know that the hardware parts, which like motherboard, RAM, processor, and all different types of parts are designed and manufactured by foreign companies like Intel, AMD, etc. So now, due to this semiconductor plants, India will be soon going to manufacture this different kinds of hardware components. So as I told you, on the software side also we are growing. Parallelly, in the hardware side also we are growing. And due to such type of development, the students, those who are pursuing, either they are pursuing in physics or science stream, they will have a lot of opportunities within 2 to 3 years. Recently only, if you heard that in Kerala, the school, one of the school introduced India's first artificial intelligence teacher robot. I repeat, India's first artificial intelligence teacher robot. So it's a very, very big revolution in artificial intelligence industry and also in education industry or education sector. And many more such developments are there on board to make Bharat as a Vikshit Bharat. Parallelly, this was the highlightment of artificial intelligence. Parallelly, different types of sectors are also available, like IoT, that is Internet of Things. IoT is a sector where all the day-to-day appliances which we use in our day-to-day life, like we use fridge, we use car, we use television, all the electronic components which are used in our day-to-day life are becoming smarter and smarter. Why? Because the sector like IoT, Internet of Things, is growing very fast. You may also have heard about smart homes, smart car, smart mobile phones, smart computer. So everything is automizing nowadays due to Internet of Things, that is IoT. So IoT is also one of the biggest opportunity for the young minds, those who are pursuing science stream. Thirdly, we are also having the blockchain technology. In India, recently, the blockchain technology is growing slowly, but within 5 to 6 years, the blockchain technology will be on the top again. So this many more such developments are going on. The reason behind this Vigyan Yatra or Gujarat Vigyan Sammelan is that to make Bharat as a Vikshit Bharat. So lastly, I would like to thank all the dignitaries, those who are present here, starting from Honorable Vice Chancellor Nilambari Ben, Joshi sir, Bhimani sir, Sahu sir, Parmar sir. Also, I would like to thank Dr. Nikesh Shah, President Vigyan Gujarat, PN Joshi sir, Mihir Joshi sir, Piyush Solanki sir, and David Drew sir. Hello, am I audible?
Yes, sir.
Yeah. So I would also like to thank all the invited speakers conveners, session chairs, event coordinators, and all those who were present here, directly or indirectly, to create such platform for all of us. Thank you very much once again.
Thank you very much, sir, for your kind words and kind notes about the Vigyan Yatra, as well as the your blessing in terms of the you're talking about the semiconductors and other things, which is very important nowadays. The Prime Minister also said about this kind of the science activities we required. So very thank you, and I hope these the informations will very much helpful to all the students who are joined over here, and also us, sir. Thank you very much. Now I'm going to introduce the one more personality from the our department only, the Professor Mihir Joshi sir. It is very fortunate for me that when you have studied with someone and he is your guru, and then after you work with him and then you are see him together in the same department. So that is very fortunate for me that I had I have studied under the Mihir sir, as well as I have worked with him, and I find lot of informations and lot of the skills by which we can improvise our activities. I'm warmly welcome to the Professor Mihir sir. There is a lot of things which I can talk about the Mihir sir, but due to time limitations, I have to say some informations about. But obviously, sir contributions in the department. He is the Professor Mihir sir is a former head of department of Saurashtra University, Department of Physics. He started his journey from the HNHB Kotak Science College, and coincidentally, that is the my college also where I have studied. So he started his journey from the HNHB Kotak. Then he's moved. He's moved to the Department of Physics, and he's work here as a lecturer, then reader, and then become professor. And then end of his journey, he's become head of Department of Physics. And in his era, we learn a lot of things. From him that how to handle the situation, all these things in research regarding. He is guided 25 MPhil students during his work in the Department of Physics. He is guided 21 PhD students and scholars, and he is get the various he is visited various internationally workshop and conferences, and he delivered a lot of expert lectures on the various themes, and his special themes on the he is working in a crystal and crystal growth. So I can say that we have one gem who developing and manufacturing the gems. So, and then after he is also received 5 national projects in a various segment. He's also getting funding from the biotechnology department also, and a lot of things he is worked in duration of the research work. He had a H index of near about 23, which is almost 1,477 citation he received in year of up to the 2018. And he is continuously working, and he is touch with us. He is working in the every segment of the research and guide the students. I'm warmly welcome you, Mihir sir, Professor sir. It's sir, you unmute your mic, sir. It is mute.
Thank you very much, Dravid Bhai, for very kind information and introduction. Thank you so much. Shall we start our session?
Yes, sir. We are
Yeah.
now moved towards the next sessions, and we starting the our sessions with the Vibhu sir.
Okay. So let me introduce Dr. Vaibhav. It's a great pleasure for me to introduce Dr. Vaibhav, very young, energetic researcher, very near by Rajkot. He is from Bhavnagar, and Salt and Marine Research Center, CSMCRI, is a very famous institute, and we had a collaboration with that institute in past, and some of our friends are still working at that particular institute. And it's a great pleasure for me to introduce Dr. Vaibhav. So let me have a brief introduction of Dr. Vaibhav. Dr. Vaibhav Kulshrestha is currently a principal scientist at Membrane Science and Separation Technology Division of CSIR, Central Salt and Marine Chemical Research Institute, Bhavnagar. He completed his PhD in 2006 from University of Rajasthan, Jaipur. Currently, he is working by exploring designing advanced polymeric materials for sustainable electrochemical energy applications and also electromembrane processes, including flow batteries, fuel cells, electrolyzers, and desalinations and various membrane-based separation and purification processes. He is a recipient of prestigious D.S. Kothari postdoctoral fellowship from UGC. He joined the prestigious Max Planck Institute in Germany to pursue his postdoctoral research work supported by DST and worked on fuel cells. That's a need of today's energy crisis. And in addition, he is a recipient of associateship from International Center for Theoretical Physics, ICTP, that is in Trieste in Italy, and a Young Scientist Award from Council of Science and Technology, Lucknow. He has published nearly 145 research papers and had 4 patents and guided 6 students for their PhDs. His studies also focus on advanced nanocomposites, nanostructured materials for electrocatalytic water splitting and capacitive applications. So it's a great pleasure for me to introduce Dr. Kulshrestha. And now I request Dr. Kulshrestha to begin his talk. Yes, sir.
Thank you. Thank you very much, Professor Joshi. And namaskar to all of you. First of all, I would like to thank to the organizer, especially Department of Physics, Saurashtra University, Vigyan Gurjari and GUJCOST to giving me the opportunity to present the work. So should I share the slide?
Yes, sir.
Okay. Yeah, so is it visual?
Yes, sir.
So thank you. So the title of present talk is Polyelectrolyte Membrane for Strategic Devising for Energy and Water System at the rate CSIR, CSMCRI. So before entering to this talk, I just wanted to introduce my parent organization. So here you can see we are a laboratory of CSIR. So CSIR has overall 37 laboratory all over the India in different cluster, 11 in biological sciences, 9 in chemical sciences, 10 in engineering sciences, 2 in information sciences, and 5 in the physical sciences. So you can see from this map, Pan India laboratory throughout from east to west and north to south, means from East Jorahat to CSMCRI, Bhavnagar, and IIM Jammu to East Trivandrum. So we are situated here at Sea Coast. You all are aware about that, and it is the main building of our institute. So CSIR, CSMCRI is involved basically on the marine chemicals and marine related activities, from saline agriculture, means from halophyte cultivation, value added products, gene pool research, to specialty chemicals regarding styrene oxides, mefrosol, ZPA, and raspberry ketones. Salt and marine chemicals means pharma grade salt, vegetable salt, salt form designing and installation, to value added waste to value, means zero liquid discharge management of different effluents, recovery of industrial grade salts from ternary and textile industry. Device and sensors means plastic chip electrode, solar thermal dryer, OLS, bacterial detection kit, improved solar salt. Marine inorganic chemicals means different type of silicate, porous materials, and many more. So I am from the Membrane Science and Separation Technology Division. We are working for the membrane designing for different application from water to energy, wastewater treatment, and others. So I just want to familiar you with the facilities available at CSMCRI. So CSMCRI has the state-of-art world-class analytical facility under one roof, and we have more than 40 sophisticated analytical instruments from here you can see powder XRD, single crystal XRD, XPS, particle size analyzer, BET, NMR, FTIR, Raman spectrometer, LCMS, HPLC, ICP, MS, and all type of microscope from transmission electron microscope to SEM, scanning electron microscope, and atomic force microscopy, and as well as with the all thermal instrument from TGA, DSC, DMA, and a universal testing machine for mechanical analysis. So now I come to the topic. So you all are aware that the global carbon dioxide emission scenario, you can see from here, it's increasing day by day. And from here, you can see from 90, in 90, India was at the 8th, 9th position, and we reached from in 20 years to the 4th position. And now around 2020, we are at the 3rd position. And the emission improved by 4 times. In this data is in the metric ton. So you can see from here, coal and lignite production, we increased around 5.7% from 19 just after 1 year from the pandemic. And also the refined oil production, it's increased 4.5% in 2021, which is 9.3% fall from 20, and increases by 5% in the next year. Crude oil production is also increases around say 1% just after the pandemic. So we need a technology with a low carbon footprint to to install for satisfying the sustainable energy goals. So one can say electrochemical energy technology satisfy the desired criteria for self-sustainability and clean energy goals. So here you can see the electrochemical energy technology where electrochemical energy play an important role, and a versatility of proton exchange membrane benefits the global sustainable energy goals. So this is the roadmap of sustainable energy technology for future. Here you can see we could rely only on the natural resources. From here you can see in this blue line, it's the hydrogen piping where we can generate hydrogen from the biomass pyrolysis. These all the hydrogen type systems. These are the wind and other renewable energy like solar, geothermal, and hydro energy. This from here you can see the CO2 which direct go to the bioreactor and convert this CO2 and combined with here this hydrogen piping and generate the natural gases which can be used for CNG fueling and such type of vehicles. We can use this. This black shows the electrical lining, and this last one is the use of ion exchange membrane. So we require ion exchange membrane. Any type of system, natural system we are using, we require the ion exchange membrane. Either we are using electrolyzer for water splitting, we require a separator as an ion exchange membrane. Short-term energy storage means redox flow battery, we require the ion exchange membrane. Fuel cell and engines, here we also need ion exchange membrane. In fact, hydrogen fueled car, we require a fuel cell where these type of ion exchange membranes used. Fueling station electrolyzer, if we require hydrogen, a membrane is a common thing that is required. So electrochemical energy is known to all of you, that we are just converting the chemical energy to the electrical energy, and this energy is total carbon free. So electrochemical energy conversion device is the fuel cell, where we can convert, we use hydrogen as a fuel and convert it to the energy. Another is the energy storage. Energy storage means we required a battery where we can store the energy and use this energy as per our requirement. Another is the generation of the energy in the form of hydrogen. So water electrolyzer is a system by which we can produce the electrochemical energy. So it's just the introduction about the polyelectrolyte membrane. So here you can see there are the two types of membrane: anion exchange membrane and cation exchange membrane. And sorry, and these both type of membranes are the selective for the particular type of ions, and it's the just a photograph of the membrane. So here you can see the vanadium redox flow battery, where this orange line show the membrane. It's the basically separator which allow the passage of protons and just stop the other ions. In the fuel cell, this blue section show the membrane, where hydrogen, when hydrogen is pumped here, this converted and just the proton pass through this membrane. In the water splitting, this here in middle, a membrane is mounted, which again separates the generation of hydrogen and oxygen. So these are the desired property of polyelectrolyte membrane, which is used for any electrochemical energy storage devices. So these are the property: membrane resistance, durability of these membranes, because these will be used in a system where a mechanical stability is required, processability, as well as synthesis. So here you can see different parameters like morphology of the membrane. Thickness plays very important role, because lower the thickness, required time is be the lower to passes the ion. Cost, raw material used for this membrane preparation, stability, strength, strain, humidity cycle, durability, swelling, and capacity in terms of ion exchange capacity and conductivity, ionic conductivity. So up to now, only one membrane is available in market, which is the Nafion, and it is supplied by the DuPont. Basically, it's a fluoropolymer type of membrane, and the sulfonic acid group is mounted in this type of membrane. So membrane is the excellent property: high ionic conductivity, high stability, hydrophilic swollen architecture of ionic channel, and high processability. But there are some limitations of this type of membrane. Actually, the main limitation is the cost of this membrane, and in worldwide only one company is manufacturing this membrane. So the monopoly is also a problem for this type of membranes, and they are using the TFE type monomer, which is banned in all over the Europe, as well as some part of US also. Synthesis process is tedious, and the crossover of fuel and electrolyte is higher in this membrane. These are the backbone, basically fluorinated backbone, and he is the functional group, sulfonic acid group. So we start from the polyelectrolyte membrane fuel cell. Fuel cell is known to all of you. I'm aware about that. So it's just the pictorial representation of fuel cell, where hydrogen fuel is inserted from the one side, and oxygen, which is present in the air, is applied from the another side of the fuel cell. And this hydrogen, by catalytic activity, it passes through this through the membrane in the form of proton, and combined with this oxygen, and final product is the water, and we simultaneously we get the electricity. Here you can see. So fuel cell technology works on conversion of green hydrogen to electrical energy through oxidation reduction reaction of hydrogen and oxidant means air. It's just the cross-sectional view of a car where hydrogen is used. So from one you can see from here hydrogen is generated. Then yes, from here you can see it's the hydrogen tank which is mounted just the seat. Then this hydrogen is fueled to the fuel cell, and then the electricity is generated and goes to the engine. The generated electricity is supplied to the electric motor. The motor uses this electricity to generate or propel the vehicle, and finally the only byproduct is the water. So the main advantage of this technology is it's totally pollution free. So it's just the miscellaneous fuel cell technology available and their comparison. So we start from the ceramic solid oxide fuel cell which operates at very very high temperature, around 700 to 1000 degrees centigrade. Then ceramic solid oxide fuel cell which operates little bit lower but higher temperature at around 600 degrees centigrade. Then molten lithium carbonate type of fuel cell which operates 50 to 200 degrees centigrade. Then potassium hydroxide fuel cell which operates around 200 degrees centigrade. Then comes the proton exchange membrane fuel cell, where a sulfonic acid incorporated in the solid membrane which used as a electrolyte. And this is the methanol fuel cell, where the hardware is almost similar, just in PEMFC hydrogen is used as a fuel, while here methanol is used as the fuel. So PMFC is preferred choice due to different advantages. Like you can see here the intermediate working temperature, better overall efficiency is better. Green fuel and water is the byproduct, and higher fuel to electricity conversion than direct methanol fuel cell due to better kinetics and proton conductivity of the membrane. These are the different components of proton exchange membrane fuel cell and DMFC. So here you can see this pink portion is the polyelectrolyte membrane, while this blue shows the catalyst on both sides of the membrane. Then then comes to the electrode. The assembly for PMFC and DMFC is almost similar. We are just introduce hydrogen here, hydrogen in this PMFC. Just from here you can see, and the used fuel come back to the cycle, while methanol is used here as a fuel. This is the fuel cell test station available at the CSMCRI. It's just the small cell is here. We worked on a 25 centimeter square and used the membrane for this system, means PM for this system, as fabricated here only. So this is the membrane which is used for the fuel cell. Basically, it's you can see here it's also a fluorinated by backbone, and a sulfonic acid group is grafted on this fluorinated backbone. This is the membrane here, and this is the polarization curve, where you can see the current density and the potential, where power density comes here this side. So Neptune gives the power density is around 412 milliwatt per centimeter square, where our membrane gives around 407 milliwatt per centimeter square. So for this we already filed a patent, and work is going on to improve the performance of this type of membrane. Another system for electrochemical is the electrochemical energy storage, where redox flow battery comes. So you all are aware that there are two types of redox flow battery. One is the classical, where all reactant and products is in the solid solution form. Another is the hybrid, where at least one is insoluble and other is the soluble. So in this, classical is also divided into two categories, where same species in both the half cells is used. Half cells means a membrane and both side of the membrane is called the half cell, and complete setup is called the one cell. So means for half cell means all vanadium type battery comes in this category. And another is the where we use different electrolyte in both the half cells, where iron chromium types of battery come in this category. So in hybrid cell, you can see zinc bromide battery is the hybrid, where lead type of battery is also the hybrid battery, and zinc air battery is also the hybrid battery. So depend upon the types of electrochemical active species, the redox flow battery can be classified in different types. Mostly all inorganic salt based redox flow battery preferred low soluble organic redoxomer due to no possibility of dimerization. So what is the redox flow battery? Here you can see the in energy storage devices, liquid active material often stored in tank energy, and another is the charging discharging. You have already seen it in the mobile phone. We charge the mobile, and after some times or after the uses for some time, the mobile get discharged. So flow battery have almost an ultimate battery cycle life, because here we are flowing the liquid which is continuously come back in the cycle. So this technology can be cycled every day for up to 30 years. So challenges for this type is battery is the scalability is a problem, because to carrying this much of liquid is difficult. Long lifespan is very good. Safety is also concern. Environmentally friendliness, cost reduction is also a concern for this type of battery, and electrolyte optimization. So here you can see a device where we mounted the electrolyte tank, then our battery cell. So we pump this electrolyte through pump mounted here, then battery cell, and finally the control system, where we can use any device. So it's just the representation of flow batteries. So electrochemical energy storage means vanadium redox flow battery. So where we convert chemical energy to electrical energy, and here you can say that no carbonization is there. So redox flow battery device use redox active chemicals electrolytes for energy storage. Cell reaction during BRB operation you can see from here. And we are using here vanadium, because vanadium is available in all four states, means +2, +3, +4, and +5. So while charging this V4 converted to the V5, where the V3 converted to the V2, and in the second step means discharging V5 goes to V4, and this V2 goes to V3. So we can identify the state of vanadium by its color. So why we are using vanadium here? A comparison table is given here with different type of electrolyte used. So the cell voltage for the vanadium is very low as compared to others, as well as the energy efficiency is very high, which is also almost equivalent to 90%. We have achieved it up to 75%. So theoretically, is it around 83 to 87%? So here outperform the battery type and system. So here you can see flow battery, that is BRV, have the with proper system designing and control, we can operate it up to the hours for a large system. So in this second graph you can see the discharge time and rated power is high for the redox flow batteries than the any other type of battery, and system power rating is also high. So in flow batteries, just after the fuel cell, the member is the flow battery. All other battery has the lower discharge time and lower power rating. These are the some features for vanadium redox flow battery. So specific energy is quite high, means 10 to 20 watt per kg. Energy density is 15 to 25 watt per liter. Energy efficiency, as I earlier told you, it's around 90% can be achieved. The time durability is 20 to 30 years, and cycle durability is it's up to around 14,000 cycle. And knobs, as I already told you, the cell voltage is quite low, which is 1.15 to 1.55 volt. So the advantage, so that the cost, if it should be cost effective, safety should be considered, longevity is shown already here, and scalability is also a problem due to carrying this type such type of huge volume of electrolyte. So BRFB supports frequent high current charge and discharge, which can be achieved hundreds of cycles in a day without causing a loss of battery performance. This first graph shows the global transition battery market from 2022 to 2029. In 7 years, it will go to the almost thrice all over the world. As well as in India, you can see in 8 years from 2020 to 2028, the vanadium redox flow market will go from 117 billion US dollar to around 700 US dollar. So it's the BRFB test station available with us. Here you can see we have 8-channel battery test station, and these are the small cell where we are preparing a cell for up to 25 centimeter square, means 16 centimeter square and 25 centimeter square. In these tubes you can see the electrolyte in charging and discharging both the states, so color change is visible here. And here you can see in this first side, in charging, V4 converts to the V5, where V3 goes down to the V2, and in discharging, this V5 goes to the V4 and V2 to the V3. These are the designing of some polyelectrolyte membranes for these redox flow batteries. So we prepare this PP type of membrane. So we first brominate this polyphenylene ether by benzyl bromination. Then after that we casted the film and quaternize this with different type of amines, and we are changing the chain length of these amines. So here you can see the membranes are stable. Stable means are mechanically stable, and we can prepare a membrane up to 30 by 30 centimeter squares for this type of devices. And these are the representation where we are using different type of cross-linking agent and modification in the chain length. These are the property of different membranes we prepared here. So this is the AEM. Common AEM is used, then DCM1, DCM2, LCSM, and Nafion 117 membrane. This Nafion 117, I earlier told you, is the commercial benchmark membrane used up to now for any electrochemical devices. So we found this LSCM2 is quite better for its performance in term of acid uptake, swelling ratio, ion exchange capacity, water molecules per unit functional group. Degree of cross-link is almost 90%, so there will be no degradation in acid environment. As in vanadium redox flow battery, 3 molar of H2SO4 is used here. And this graph shows the Nyquist plot. Nyquist plot means it's just the impedance spectra for real and imaginary part, from which we can calculate the cell resistance. So lower cell resistance means higher performance of the membrane.
Sir, the screen is not visible.
Yeah. Hello. So these are the performance means polarization curve for these 3 membranes in terms of their vanadium redox flow battery. So we operate this system at different current density from 50 milliampere per centimeter square to 150 milliampere per centimeter square. And this last graph shows the efficiency of this cell. Efficiency means Coulombic efficiency. So at 100 milliampere per centimeter square, we are getting a quite good result, with where the current efficiency is higher, almost 10% higher than the Nephron, than the voltage efficiency and energy efficiency. Long cyclic for these systems are also run for here. These are the number of cycles. So we operate these systems for different cycles and to check the deterioration in the performance. So almost similar performance we achieved up to 50 cycle. In fact, we perform these results up to 300 cycle to 500 cycle, but there is no change in the performance. In fact, what happened after some time the electrolyte defading of electrolyte gas started due to diffusion of vanadium. So diffusion of vanadium is also a major problem which can be resolved. So here it's also written here. So electroosmotic drag at higher current density cause electrolyte imbalancement, reducing the thickness of membrane to overcome the overpotential issue and acquire the same specific capacity at lower charge discharge potential. And the improved efficiency is also required. We have achieved up to 75%, but it should be more than 85%. In another piece of work, we also prepared the membrane. Basically, these are the interpenetrating network type of membrane, and these membranes are also used for these vanadium redox flow battery type of system. So here you can see the 3 membranes, B, C, and D. So ACIPN 153 is the membrane where the thickness of the membrane is 150 micron, and we functionalize this membrane for 3 hours. Where ACIPN is the same membrane, we functionalization time is little bit higher, and we reduce this thickness from 150 micron to 120 micron. As I earlier told you, as reduce the thickness, resistance of the membrane will be lower. Oh, sorry. These are the chemical characterization of the membrane. So here you can see around 2800. You can see the peaks for these are the basically FTIR spectra, means ATR, FTIR for IPN membrane, and here you can see the functional group of presence of sulfonic acid group. This in red, green, and blue. While there is it's the film just before the functionalization. These are the cross-sectional and surface view of the polyelectrolyte membrane. So the membrane is almost smooth. So there is no cracks and holes from where the electrolyte can pass. And the presence of vanadium, we also optimize the membrane after the cycling of after this vanadium cycling, and presence of vanadium is found on the surface of the membrane. These are the just the physicochemical parameter for these membranes, where you can see the proton exchange capacity is almost similar for all the membranes, and this vanadium ion uptake is almost means in this nephron is much higher. So we don't want this uptake of vanadium in this membrane. So we try to reduce the vanadium uptakes in our membrane. These are the Nyquist plot from where we calculate the resistance of this membrane in a cell. So this ACIPN shows the lowest resistance of the membrane. These are the polarization curve for the nephron and our prepared membrane. So this membrane shows the better performance, means almost 6.06 into 10 to the power 4 volt per minute efficiency. In fact, we test this membrane for long-term cycling, and as I earlier told you, what happened after 100 cycle, the fading of this electrolyte get start. So we need to balance the electrolyte by mixing both the electrolyte together, and again starts the experiment. So we performed these experiments up to 300 cycles, and these are the polarization curve where we are getting much better result than the commercial available membrane, which is Nephron 117. So these two membranes are very good for this type of redox flow battery. One more membrane is also fabricated for the redox flow battery. Basically, is the fluorinated backbone type membrane is prepared here. So these are the just the IR and NMR to show the confirm the preparation of the polymer. Then from introduction of the functional group in this polymers. Here are the basic characterization or physicochemical properties of the membrane. So here this PVDF grafted sulfonic acid 15 membrane shows the better performance in all the comparison of the membrane, and resistance is quite lower. We optimize this membrane for with the different applied current density from 50 to 150 milliampere per centimeter square. So the objective of this type of membrane is just to improve the discharge time of the battery, so that we can get the proper efficiency with these type of membrane. So in polarization curve, we get around 250 milliwatt per centimeter square with this membrane. Sorry, the 280 milliwatt per centimeter square with this membrane. So peak power, just the peak power density. So in all three membrane, this last one membrane was quite good to compare in comparison to all three, as well as that was good. That was also better with the commercially available Nephron 117 membrane. We are trying to prepare a large stack for the preparation of this type of battery. It is in under process. Another is the electrochemical energy system for hydrogen production, means water electrolysis. So it's just the representation how we can get the clean hydrogen, means green hydrogen, if we use the renewable energy. renewable energy to split the water. The hydrogen, the generated hydrogen will call the green hydrogen. So here one can see it's the very old reaction. We just use the two electrode and dip it in water and applied a potential, so water splitting get started, and we get oxygen on the one electrode and hydrogen in the another electrode. But here the applied potential is much more higher. Required applied potential is much more higher. So after 1917, a zero gap type of electrolysis cell is prepared, where a separator is used here. Then anode and the separator is just sandwiches between the electrode. So here required energy is little bit lower than this previously reported type of electrolysis cell. Then the third one is come in the picture after 2010, where we are just using electrolyte in one side, means water in one side, and in another side we are just getting the direct gas, means direct hydrogen production. This type of cell is called the asymmetric PEM electrolysis cell. The water is converted to hydrogen and oxygen through this process. The net utilization of hydrogen from electrolysis is fuel cell. It goes to the fuel cell and other self-sustainable energy technology. Is just the component for this electrolysis cell. So it's the PEM electrolyzer where proton exchange membrane is used. Then it comes just a catalytic layer which converts this hydrogen to the proton, and then the electrode from both the side, and from once we just put water from the one side and get the water and oxygen generated here, while on the another side, another electrode we get the water and hydrogen, and we can store this hydrogen after removing this water, means after dehumidification, the hydrogen can be used in the fuel cell. It's the another type of electrolyzer which is called the alkaline type of electrolyzer, where another type of membrane is used which is the anion exchange membrane. So the advantage of this anion exchange membrane type electrolyzer is here we use the low cost catalyst, while for PEM the higher cost platinum based electrocatalyst is required. So we prepared a membrane for this type of system also for water electrolysis. Basically it's a PVDF based membrane. So functionalization of PVDF is really very, very tricky and difficult. So we just created some free sites to functionalize this with the sulfonic acid type of group, and used a very strong acid, means chlorosulfonic acid, to functionalize this film and convert into the membrane. And these are the polarization curve we compare. So the amount of this sulfonic acid group varied by the time duration. So we prepare this OPVDF 15, 20 and 25 type of membrane and compare this with the benchmark membrane. And in this second graph you can see the stability. These are the stability data for this membrane. So we are getting the good potential which is not exactly comparable, but we will improve this. This is the pictorial representation of the membrane after delaminating. So here membrane electrode assembly is prepared for this water type of splitting. So here you can see the Grotus mechanism is followed to transport of proton across this membrane. This is the actual picture of this electrolysis system which is installed at our place, and I just want to show this video. So hydrogen is generated here, and the bubble you can see in this beaker. So continuous generation of hydrogen can be seen from this video. So you all are aware that in January 2023, our Prime Minister launched the hydrogen mission in India. The cost of that hydrogen mission was around 19,000 crore. And now different companies comes in the market to prepare the electrolyzer. These are the cutting of newspaper in this month only. So recently, NTPC installed a electrolyzer. It's the actual picture of electrolyzer. You can see here. It's a very big size. It's the capacity of this electrolyzer is around 1.6 megawatt, and two electrolyzer installed in the NTPC renewable campus in Greater Noida. And these electrolyzer can generate 260 kg of hydrogen per day, means 10 hours during the day, means they can generate 26 kg of hydrogen per hour. In this series, Larsen and Turbo installed its first electrolyzer, which is made in house in India using licensed McPhy technology. Means Larsen and Turbo is just assembling this in India. The company supplied from this is the France-based company. So Indian engineering company Larsen and Turbo has announced that it has commissioned its first electrolyzer, which is made in India. So this McPhy is a French company which supplied all the part of this electrolyzer. So now I come to the second segment of this talk, which is the water. So as I earlier told you, we are working for membranes for water and energy devices both. So there are different type of membrane, you all are aware, and we are working on all types of membrane. So first is the microfiltration membrane. These microfiltration type membrane just remove the bacteria and suspended solid from the water and allow the passage of all the ions and viruses across this. Second type of membrane is the ultrafiltration membrane, where the size of the pores is 5 to 120 nanometer. These just restrict the virus, bacteria, and suspended solid and allow the passage of water and all the ions present in the water. Then comes in the nanofiltration, which allow the passage of water and monovalent ion. Monovalent ions means sodium chloride, while it stop or reject the multivalent ion like sulfates. Then comes is the reverse osmosis, commonly known as RO. Basically, it's the totally dense film, and it just allow the passage of water across this. So the way we are working for all type of potable water and wastewater treatment. In fact, removal of contaminants like fluoride, arsenic, argon, and iron, and others. So here you can see different type of or different grade of water we treat here. So approximately 0 ppm water, which we used in our laboratory or pharmaceutical industry or semiconductor industry, which is the ultra pure water. So electro deionization technique is used to generate this ultra pure water. Another is the water where the TDS is 400 to 700 ppm. So for this we just required a microfiltration or ultrafilter type membrane. Then comes in the nanofiltration type of the membrane. After that, where the salinity is low, means brackish water type water is present. So treat this type of water, we need RO system, which is called the brackish water RO, and it's just the 4040 and 8040 is the size of the module. And last one is the seawater desalination, where high pressure where the high pressure is required to remove the water to get the potable water. Another type of the membranes are the ion exchange membrane. I have already discussed for energy devices the ion exchange membrane. This type of membrane is also used for water desalination by the electrodialysis techniques. So we are involved for different segment of membranes, means flat sheet membrane for water purification, desalination, ultrafiltration, nanofiltration, reverse osmosis membrane, membrane for energy application, membranes for specialty application, means to remove the contamination from pharmaceutical grade product or other, or membranes for wastewater treatment. It's just the overview of different type of membranes. So here it is the basically microfilter type membrane, which is a hollow fiber membrane. So here you can see it's the hollow fiber making machine, and these are the hollow fiber where the size of this hollow fiber is around 500 to 600 micron, and outer diameter is around 1000 micron, means around 1 mm. So this type of module institute prepare, and we also already transferred this technology to this Uniflex membrane LLP, and they are producing this microfiltration type membranes. As I told you in last slide, this type of membrane is used to just to remove bacteria, virus, and suspended solid. Another is the flat sheet ultrafiltration membrane. It's also a same type of membrane, ultrafiltration membrane, where one can remove the bacteria by 6 log and virus by the 4 log reduction is possible by this. Commercial production scale 1 meter width and up to 200 meter length can be prepared in a one round, and this technology has already transferred to the Uniflex membrane Pune, Rinjai, Ahmedabad, and Omtech company based on Rajkot. So ultrafiltration is a way forward for water clarification and purification. Then a nanofiltration type membrane is also prepared by our institute. So here we can remove the bivalent from the monovalent by this this technology. So we can also remove the dye from the wastewater by this. So here you can see the colorless water in this vial by nanofiltration. Then the last is the RO membrane. So RO membrane fabrication facility is available with our institute. Is the first is the casting microfiltration type membrane is casted on the bottom. Then a separating layer, polyimide layer of few nanometer is casted on that polysulfone, and these are the module making facility available at the institute. So commercially production scale is 100 to 300 meter square membrane per batch, and it's just the representation where a polyester fabric is used. On polyester fabric we casted a porous polysulfone layer, and it's just the ultra thin membrane of 200 nanometer, which remove the all type of suspended solid and salt present in the water, and we get the pure water. Last one is the ion exchange membrane. So ion exchange membrane, basically preparation of ion exchange membrane is the 3-step process. We first prepare the polymer, then we convert this polymer into the thin film by the blow film extruder, and finally we functionalize this membrane in large columns to get the big size of membrane. So we use the chlorosulfonic acid to convert this film into cation exchange membrane, and for convert the membrane into anion exchange, we functionalize it, we brominate that membrane, and followed by the quaternization. So it's the principle of electrodialysis. So plate and frame type of system is designed for this type of water desalination system, 2 electrodes is used at the end of the unit, while alternate cation and anion exchange membranes are placed between these units. So 100 to 120 membranes means 240 membranes can be placed here, and we can prepare as per requirement of a domestic or community scale type of unit, and with a capacity from 20 liter per hour to 1 meter cube per hour, means 1000 liter per hour can be enhanced. So by this, the advantage of this type of electrodialysis system is we can manipulate the presence of ions. As you all are aware that this is the ideal concentration of water, feed water, where the TDS should be 300, around 300 to 500 ppm. So the major constituents of water is the sodium and chloride, which is not good for human health. So while the other ions like magnesium, potassium sulfate and bicarbonates are required. So by manipulating these membranes and using this electrodialysis type setup, we can get the mineral enriched water, simultaneously desalination as well as mineral enriched water. So the power consumption of this unit is around 0.7 kilowatt hour per kg of salt removal, while the current efficiency is around 86 to 88%. These are the societal work done by the CSMCRI. So we recently installed a plant near the coast. So this plant operated on solar energy, fully on solar energy, and fulfill the requirement of 1,000 peoples of the blazers. So present now it's come to the end. So acknowledgement is I would like to thanks to Dr. Karnan Srinivasan, Director CSIR CSMCRI, Professor Ramanujan of IIT Madras to help the setup of vanadium redox flow battery. The all work is done by the students, so they are acknowledged, as well as all the funding agency. So thank you very much.
Wonderful talk, sir. You have covered all the aspects, and you have also given the different type of membranes and how those are used for electrochemical cell, even for the today's energy crisis based on hydrogen fuel. And the government of India is promoting this. And two big giants of our Indian companies, they have invested, and they are also going to invest their funds into the green energy sector. And
Yes,
even
sir.
for the
Both Adani and Ambani,
Yes,
Reliance
yes,
is interested in this field. In fact, the 20 companies of India is come forward in this field.
So you have rightly selected today's topic for our young generations. They will get inspired to work in this particular very hot field, and which our nation needs at a particular level. And also, we are very glad that you have shared your technology to companies, one in Rajkot and another in Ahmedabad. So
Yes.
that's really remarkable, sir. So now I ask this audience if they have any questions, they can ask.
Yes, sir. I have one questions with you, sir.
Yes, please.
Sir, your presentation was so nice as well as so informative, and the work you have done on the membrane, that membrane technology is remarkable in the every terms for the industries as well as for scientific phenomena also. Yes, definitely. I had also some experience little bit in the membrane technology that we try to prepare the electrolyzers. As we are knowing that in a market nowadays, these Kangen water machines called as one kind of electrolyzer is are there. So we have prepared it at our department with the using of platinum coated titanium, and then we used that membrane also, the anionic exchange membranes.
Ji.
So there's a lot of information I'm getting today about that, and obviously we can improvise our membrane also.
In fact, we can collaborate some work.
Definitely, sir. That is a very thank you for that word. That we looking someone who have a good expertise in the membrane actually. That we had used the cationic membrane at that time, and then we are also using some doing experiment on the anionic membrane, and then we have to prepare that electrolyzers, and then we have manufacturing the complete setup of that at our laboratories in Department of Physics, sir. But that is a very nice or informative talk for, especially for me, that I can get some more information on the membrane, sir.
So actually, Dr. Dhruv, we have all the facility available with us, so you people can use that facility too. So absolutely no problem.
Thank you very much, sir. That way, I hope we can do a lot of things together.
Sure, definitely.
Thank you very much, sir.
Any more questions? If no questions are there, let me thank today's speaker for giving a very nice talk. And also, I'm thankful to our young faculty members. They have also explored collaborative work with our distinguished speaker. So let me thank today's speaker, Dr. Kulshrestha. Thank you very much for spending your valuable time. Thank you very much, sir.
Thank you very much, sir.
Today's another speaker is from the same institute, and it gives me a great pleasure to introduce him. Again, very young and dynamic researcher, and his name is Dr. Subhadeep Neogi, and he obtained his PhD from IIT Kanpur and presently working as a principal scientist in CSR, CSMC CRI means Central Salt and Marine Research Institute at Bhavnagar, which is very near from Rajkot. It's sir is working in our neighborhood, and he has published 2 book chapters and published 75 research papers in very reputed journals. He is a recipient of Humboldt Fellowship, DST Early Career Research Award, and RSC Outstanding Reviewer Award, and listed as world's top 2% scientist in 2022 by Stanford University and elsewhere. So it is a matter of pride and prestige for us that Sir is a very distinguished young researcher. Dr. Neogi is a Life Fellow of Humboldt Foundation, Indian Chemical Society, Chemical Research Society of India, and recognized as top 3% cited ACS author in 2022 for all publications from India. His research interest focuses on energy generation, pollutant monitoring, CCUS, and heterogeneous catalysis using crystalline porous materials. So, Sir, interest is very diverse, and it is also pertaining to the demand of our nation. So, I request Sir to give his part. Dr. Neogi, please.
Yeah, am I audible?
Yes, sir.
Yes, share my screen. Okay, is it visible?
Yes, sir.
Okay. So first of all, I thank Professor Joshi for the nice introduction, and it is indeed a great honor and pleasure to be here as a part of lecture series in Vigyan Yatra and by the Department of Physics, Saurashtra University, Rajkot. And I'm thankful to all of you who has done a great effort in this journey. So coming back to my today's presentation, actually Dr. VIBHA Kulshrestha just gave a nice talk on membranes and all over the institutes. What membrane science is doing excellent actually. Now I will be presenting a little bit different. Just a moment. I'll be presenting a little bit different on materials chemistry, and specifically those materials which are advanced and porous and crystalline. So that is why the title of my talk is Programmable Porous Material. That is a versatile platform for environmental remediation and sustainable catalysis. So before I talk, as Professor Kulshrestha also told, that this is where our CSM CRI is located at Bhavnagar, Central Salt and Research Institute, also known as Central Salt and Marine Chemicals Research Institute, CSM CRI, where we are working in different research and development verticals, starting from marine products and processes like salt, water, marine chemicals like inorganic, organic, natural products, and marine elements. Also, we are working on marine biology, where marine aquaculture of seaweeds, macroalgae, and all these are done. Marine environment-related research mainly deals with marine pollution, their assessment, and different other sectors. Now, as you already know from Professor Kulshrestha's talk, that he has licensed so many technologies to different parts of India. So here are some of the technologies related to salt and marine chemicals: high purity salt, low sodium salt. Whereas inorganic and organic chemicals, I'm more keen into this division because I work for this division. So zeolite A, precipitated silica, and also 2-phenyl octanol in terms of catalysis, polymeric ion exchangers, and these are the inorganic and organic materials. Waste to wealth has been also developed, like zero liquid distillate process and marine biology and all this. So these are some of the collaborators, licensees and partners that we include in CSMCRI. Already shown, but I want to show you more on this. We have a very good instrumental facility under centralized facility in AET SIF department. We have more than 40 sophisticated analytical instruments, and we are thankful to them. Because of this, our research and our technologies are developed. So TAME, FESAME, and NMR, single crystal X-ray diffractometer, powder X-ray diffractometer, all these are very important instrument in our research. Specifically, I will talk more about single crystal X-ray diffraction and powder X-ray diffraction because it is more to my research areas. And there are various scientific research and development divisions: analytical division, applied phycology division, and I'm working in inorganic material and catalysis division specifically. So where we are developing materials and different porous materials for different applications that I'll be showing some of the tales of the story. So this is the inorganic materials and catalysis discipline team. We are working total 9, actually, including our head, Professor E.S. Subramaniam. So we are working in different fields, but our goal is same. Like I am working on porous materials, Dr. Ankush Biradar is working on different other materials, mixed metal oxides, and Dr. Govind Setia is working on zeolites, Dr. Joy Mitra is working on gels. So we have a lot of expertise, and all of them have very unique and very reputed academic background. So coming to my group, here my small research group works on called framework chemistry group. We are working on advanced porous materials. Now, what are advanced porous materials? These are materials that have generated not long back. These materials generated only in 1990s, and some of them are even developed in 2005 or something like that. So they are kind of new generation materials. So these are called metal organic frameworks and covalent organic frameworks. So my group works on these porous materials for different applications. So we are working on multidimensional metal organic framework, in short MOF, and covalent organic framework called in short COF, and they are post-functionalization and they are reconfigurable composite for various applications like adsorption and catalysis, energy storage, energy generation, switchable chemosensor, water harvesting application, anti-counterfeiting application. These two topics are covered most, and also pollutant detoxification. So not only that we are making them in lab scale, but we are also putting them in real-time scenarios like MOP sponge. We have developed MOP fabric. We have developed for different applications for separation purposes and for adsorption purposes. We also develop metal organic framework based membranes, and not only that, we have also developed them in bulk scale, like in kilogram quantities or something like that. So these are some publications that we realized in So what for that we have taken two paints. So these two paints are dispersion of pristine mauve and terbium doped mauve respectively under daylight. So you see no changes in the color. However, interestingly, when we expose visible UV light in this pen with a 365 nanometer UV light, we see a difference in color. That is one in green, that is actually it is pristine mauve solution, and this one is terbium incorporated mauve that is showing green color. Okay, so with that we made or we wrote an acronym in a white paper. Actually, we wrote the acronym of our institute, CSMCRI. So you can see this is invisible level under daylight. So there you cannot see anything. But if you expose with this same UV light, you can see CSMCRI is clearly visible. So visible fonts under UV light for anti-counterfeiting application, where we have used C with that intrinsic mauve, S with terbium doped mauve, and alternative way. So this has been used for anti-counterfeiting application for further technology. And this is another work in line of this, a water harvester framework for triphasic detection of organotoxin with site memory reliant security application via pH trigger flow sensing. So this we published 2021 ACS Applied Materials. So this is the overall scheme of formation of this mauve. Here we have taken two different ligands. This is ligand having large aromatic core, which is hydrophobic in nature because of large aromatic cloud, pi cloud. So hydrophobic roof. So this is fluorescent core also, and organic guest interactive sites. On the other hand, we have taken another pyridine based ligand, which is having a guest interactive sites. These are polar in nature, so it is hydrophilic in nature, so hydrophilic pillar. So when we combine this in presence of zinc as a transition metal ion, we form a CSMCRI 6 framework, which is like that. You can see the overall structure. These all are from single crystal X-ray diffraction data. So we solve the structure here because we have the expertise of our group is having expertise of solving the single crystal data from single crystals and interpenetrating and interpreting them in for different applications. And we have different softwares also where we can make these images from single crystal data. So this is twofold interpenetrated pillar layer mauve, which shows porous nature. Okay, so we have shown that framework stability in diverse condition, whether our mauve is stable or not, it has to be clarified. So this is actually the CSMCRI 6 where we get experimentally. This is in open air for 6 months. You can see that there is no change, so it is stable in pH 7.5 HEPS buffer in weakly acidic and basic condition after up to 12 hours, and in water for 6 months also it is stable, perfectly stable. And we have measured the surface area. What is the porosity of this mauve? We have measured from nitrogen adsorption at 77 Kelvin temperature, and we see that it is having a microporous nature, and surface area is having almost 14 meters square per gram, which is huge in nature. Also, the material, as I told, that is having some hydrophobic nature. So when we put a drop of water, it does not get loaded or it does not get flooded over the surface because of this hydrophobic nature. This is the how we expose the mauve towards moisture. We take a small beaker and we keep this small beaker into large beaker containing water, and we heat it, and all the solvent molecules goes inside, and we see that in water for 30 days, in water for 60 days, or up to 180 days, that is up to 6 months, it is completely stable in nature. So after that, we also checked whether it can take up some water or not. In water vapor adsorption studies for that we have done, and we see that a shaped isotherm, this is very important for water vapor adsorption. If the water starts taking from here, that will not be considered as a good water absorber, because after reaching a particular pore, a particular pressure, the overall water uptake increases. So S-shaped isotherm is formed with steep pore filling state around P by P0 is equal to 0.5. That is, it is having a relative humidity of 50%. the water uptake is occurring, and it can have a maximum water uptake capacity of 0.36 gram per gram, which is huge in nature. So we have also found that there is negligible hysteresis. You can find that absorption and desorption curve does not vary much. So this is favorable for material regeneration during multicyclic performance, and we have indeed performed the multicyclic water absorption performance, and we see that it is completely recyclable in nature up to 6 cycles. So this is the pristine, and after that we have made, so up to 6 cycles there is no problem without restoring the complete water harvesting. So how to use that for real-time application? So we have probed this particular metal organic framework for real-time potential in atmospheric water harvesting. What we did, we left the MOF powder overnight over the roof of our lab, and in the next day we kept it inside the vial and heat it, and we found that water droplets are formed. So when we keep it on the roof of our lab, then there was no moisture inside this MOF, but it takes automatically from the moisture of the air and it forms, and when we heat it, the water is getting regenerated. So in a sense, CSM-6 can be acted as a atmospheric water harvester, where temperature triggered porous sponge behavior is evidence, in a sense that at low temperature it captures the water, and at high temperature it releases the same water. So it is very important for water harvesting application. Now, as I told, that my research glimpse or my research focus is somewhat on the basic side of this research also. So you also wanted to know that what is happening inside the MOF, because of which it is showing water harvesting application. So we have a snapshot at the molecular level. So this is the atomistic snapshot of sequential pore filling of water inside the MOF. We can see that when 10 water molecules are getting inside the pores of the MOF, it is showing like that. And as we increase the number of water molecules inside the MOF pores, we see that it increases, number of the molecules increases inside the cavity. Now, affinity of water towards the polar pillar, because I have initially told you that the pillar of this MOF is hydrophilic in nature, whereas the roof is hydrophobic in nature. So it is acting in the same way. It is attracting the water molecules towards this, and because of that we have some little bit of pillar distortion. We have also measured that how much pillar distortion on going from original MOF towards 30 water inside the cavity. So we see a very not much, but some kind of distortion is there. But because of this distortion, the MOF is not at all getting cleaved or getting destroyed. So hydrogen bonding interaction between the MOF functional sites and incoming water increase the water, results angular distortion between the adjacent pillars because of its rising affinity towards DPTA linker. DPTA linker means this one. This is called DPTA linker, which is also a hydrophilic one. So after that, we have used this same MOF for triphasic processing of nitroexplosive pesticide, aniline and nicotine. So this is a huge amount. These are having huge noxious and very bad impact over the hydrosphere as well as environment, because pesticide, aniline, nicotine and nitroexplosive specifically, that TNP, trinitrophenol is an explosive compound. DCNA, dichloronitroamine, is a pesticide, and amine and alkaloid are also inherently toxic. So we can see that this MOF particle or this MOF can selectively detect TNP, DCNA and amine and alkaloid specifically from other components. And we see that selective, fast responsive and nanomolar recyclable detection of 4 classes of organotoxin. Their high quenching constant we have calculated from fluorescence spectra. The quenching constant is in the order of 10 to the 5 to 10 to the 6 mole inverse, which is very high in nature, and ultra-sensitive detection because of ppb level limit of detection in water. So we have also checked the recyclability of this material towards sensing of these pollutants, and we see that pristine intensity of the MOF remains unaltered after regeneration. So this can be recyclable in any time, anywhere. So not only that, we also wanted to see whether it can detect all these pollutants in vapor phase or in solid phase, and that is why we call it a triphasic, that is three-phase, in solution, vapor, and solid. And we can see that bright blue MOF emission reduced by all four analytes in the gaseous phase. So this is the way we diffuse these toxic pollutants over the MOF. Here we have TNP solution. Here we have a nicotine solution and dichloran pesticide and aniline solution, and we expose it towards the MOF, and we see a distinct color change. Also, in presence of these four pollutants, we see that a visual colorimetric change is occurring. That means it is detecting all these contaminants. Now, this is a just a moment. So you can see this is a video which shows that this is the MOF solution. When you put a slight amount of DCNA, all the glow immediately goes. On the other hand, this is also another pesticide which we use, and the initial glow completely goes after one drop. So that is how excuse me, is the slides visible? Hello?
Yes, sir.
Okay. So this is the on-site detection of pesticide contamination which we have done over the cabbage leaf, because we know that in cabbage production lot of pesticides are used. So that is why we have used that. We have used a normal cabbage leaf where we put our MOF solution. It looks under UV light, it is a bright blue emission. But whenever a cabbage leaf is having pesticide, immediately the bright blue emission goes away. So that means that this particular cabbage leaf is having pesticide contamination. So again, we have used the same MOF solution, and it regenerates because of regeneration. So that is detectable in nature. So what happens? The characteristic blue glow of the MOF over cabbage leaf intensity reduced in presence of dichloran pesticide, and the emissive glow is immediately recovered upon addition of one drop of MOF dispersion over the turn knob position. So that means that it can be reused over time, over multiple cycles. So now to find the mechanistic detail, what is the actual molecular level scenario of this? So these are the molecular structure of trinitrophenol, trichloran, aniline, nicotine, and this is the molecular structure of our ligand, as I told you previously. So we see that spectral overlap between absorption spectra of analytes and MOF emission, and this is the optimized structure of metal organic framework in presence of different organotoxin. Here it is in presence of TNP, which goes and shows several hydrogen bonding interaction with the pendant functionality of the MOF. Here it is also showing in case of dichloran, and in case of aniline, it is showing that it is inside the channel and showing hydrogen bonding interaction with the polar sites in the MOF. And in case of nicotine also it shows. So that is how the interaction is going on, and that is the reason that why this quenching is happening. So next, we have used the same MOF for pH trigger fluorescencing, a visual proof to donor acceptor synergism. Now you can see that this is actually the MOF coated filter paper which show bright blue emission. Now you see this is HCl and this is NH3 vapor. What happens when you put inside of both of them? So when we put in HCl, you see that the bright glow goes off and it is kind of dark color. When on the other hand, when you put the same filter paper over the NH3, the bright glow emission again come back, and it is reversible up to 30 cycles, so that dipping and going off and going on can be done several times. So with that in knowledge, we also did over a cuvette, and you see that reversible acid-base trigger flow switching in liquid phase is also possible. We give this MOF solution to concentrate HCl, all the emission goes off, aqueous NH3 again turn on, is coming back, again concentrated HCl we give, and it is coming again going off and again going on. So in this way we have done up to 18 times, and we have seen that it is completely reversible in nature. So with that in mind, we have done acid-base triggered security ink. In the same way as we did for other paper, other work, that is mock dispersion with filter with pens, and we write CSM serai with this, and it's in presence of UV light, it glows. And when we give the concentrated HCl vapor or normal HCl vapor, all the letters completely goes off. This we call a protonated encrypted state. And when we give this same paper to aqueous ammonia vapor, then we call it a deprotonated decrypted state. All the letters come back. We have also done this over a currency note. You can see in presence of, we have written a word 6 with this pen, and this is visible under UV light. But when we add it in H+, that is protonated encrypted state, all this 6 color is going off, and in presence of OH-, that is aqueous ammonia, it comes up again. So for that we have also, I'll also show you one video where this is the 6 color, and my student is dipping over H+, that is HCl vapor, and you can see that the HCl, this 6 color is completely gone. And when we dip it over NH3, we can see that the 6 is again coming back. Yeah. So in this way, this is the fluoro triggered acid-base triggered security ink, and we have, as I told you, that my intention is to show what is actually going on inside the framework for this phenomena. So we have done luminescent defect pair in self-calibrated linker. Why this is so? This is the part of the aromatic ligand that you used in MOF synthesis. So it has this center as well as this NH2 center, but in presence of H+, because of higher pKa value, this part actually gets protonated, and we see that a disrupted conjugation is happening. Because of this disrupted conjugation, all the framework color or the framework intensity, blue intensity, immediately goes off. Now when we give that OH-, this proton is scavenged, and it comes back to the original state, that is that conjugation is repaired back. So HCl protonates the linker nitrogen atom, it disrupts the MOF conjugation and quenches the emission. On the other hand, immediate deprotonation by NH3 repair back the conjugation and restores the PL intensity. So this is how we have demonstrated the anti-counterfeiting application, and you can also find it over our CSM serai homepage, where we have made quick detection kit for aqua contaminant detection anywhere and anytime. So this is the background of our work. You can find it over the CSM serai webpage. Now coming to a different aspect, that is in situ fabricated cellulose composite in a hydrogen bonded MOF for flow switchable biphasic tweezer. The rationale behind this work, we published this in a few years ago in GMCA. So the synthesis of nitrogen rich MOF. Why nitrogen rich MOF? Because nitrogen is a functionality that can attract many of the guest species because of its polar nature. So with free functionalized ligand, chemical robustness and bulk scale synthesis of the material is also important. We are also looking for utilizing functional starts for pollutant detection and complete composite fabrication of real-life application. So to this end, we have made this MOF starting from normal amino terephthalic acid, which is a well-known linker found from any chemical lab in kilogram scale, and we have used the same linker that we used for the previous work. In presence of cadmium, it forms a CSM serai 14, which is a two-dimensional structure, and here we can see that free NH2 group is affixed inside the pore. This is another view of this MOF, which shows the two-fold interpreted curved layer structure, and hydrogen bonding is existing in the stacked and interwoven layers. OH, NH, CH, and NH pi interactions are there present. So we have used this MOF in large scale, probably up to 10 gram scale, and we have also made it over different activation condition like in buffered solution, in acidic and weakly acidic and weakly basic solution. And we see that the MOF is also boiling water and chill water. And this MOF is very stable in all the harsh conditions. So it is very stable MOF in a sense. Not only that, because Gujarat is very famous for cotton production, so we thought that why not make this over cotton, that is cotton fabricated MOF. So we have in situ grown the MOF over cotton fiber. So this is the different same images of the fiber before and after MOF doping, which shows the formation of the MOF particle over the cotton fiber. And we have also corroborated from the PXRD pattern that this is the commercial cotton fiber, which have no other peaks except for these two peaks. And this is the CSM Sarai 14 grafted cotton fiber, which shows that presence of as made CSM Sarai 14. So this means that these MOF particle have been grown over the cotton. So why use of this, I will tell you later. First, we made ultra-sensitive and recyclable detection of reactive oxygen species that includes chlorate, ascorbic acid, H2O2, and singlet oxygen, and OH radical, and ascorbic acid. So we see that it is particular for mainly for chlorate, hypochlorite, and ascorbic acid, and ClO minus is more showing the turn-off detection. And we also saw that from Stern-Hormer equation, the KSB, that is quenching constant, is very high in both the cases, and LOD value, limit of detection value, is also in the ppb level. So it can easily detect and very sensibly detect both the pollutants. Okay, this is multicyclic in nature because we see that the sensing of ClO minus is recyclable up to 5 cycles. Also, after the cycling studies, we see that there is no degradation of the framework as we corroborate from the PXRD pattern. Now, we see that anti-interfering and fast responsive sensing of these species. You see that here that a higher concentration of interfering analytes at 45 micromolar, it is having no change towards the MOF PL intensity, whether in presence of ClO minus on ascorbic acid in much lower concentration, there is 20 micromolar concentration, it immediately quenches. So it is competitive towards or it is selective towards ClO minus and ascorbic acid. And we also see that it is fast responsive. Just after 20 seconds, the maximum quenching is happening. The maximum quenching is happening. That means that is fast responsive in nature in 20 seconds. So it is fast responsive and anti-interfering. We also see. Now the interesting thing of this MOF is that the fluoro-switchable reactive oxygen scavenging by host gas mediated luminescence variation. In the earlier slide, we just saw that both the chlorate and ascorbic acid are having this quenching performance towards the MOF. Now, here you can see the opposite effect. When we use this MOF for chlorate, it immediately turns off. But in presence of the same chlorate and MOF, when we add the ascorbic acid to this mixture, it is working as a turn on. Fluorescence is turning off by ClO minus, but slowly when we start adding ascorbic acid, it is getting turned on. So it should not be the case, but it is happening here. So addition of ascorbic acid to MOF plus ClO mixture resulted PL intensity rise. In contrast, usual quenching occurring where H2O2 and ascorbic acid mixture is given to that. Expected lowering of emission intensity when ClO minus is added to ascorbic acid. And after that, we also saw that on-off-on flow switching in cuvette, where we added ClO minus to this, and we saw that gradual turn off. But when in the same mixture, when we add ascorbic acid, it is getting turned on. So here in filter paper or paper strip method, we also saw that kind of ClO minus detoxification, that is, it is scavenged. Okay. Now, regeneration of the material through neutralization of hypochlorite from MOF pores. So here we see that MOF powder also turned brown upon adding ClO minus, and it fainted slowly to white when this ascorbic acid was used to that. So addition of ascorbic acid to the same spot regenerated the original emission of metal organic framework at the rate cotton fiber. So here is the colorimetric switching of MOF at the rate cotton fiber, which shows that the cotton fiber is also changing its color depending on the addition, selection, or how you are adding this ClO minus and ascorbic acid. So when you add ClO minus, it is getting dark in color. When you add ascorbic acid, it is getting fainted in color. So because I am more interested in how it is happening, so flow switching mechanism and molecular tweezer concept we have developed. So we see that from overlap that UV visible spectra of none of the ROS, reactive oxygen species, or ascorbic acid and MOF solution shows no overlap. Okay, that means that resonance energy transfer process is not operating. On the other hand, when we see that photo-induced electron transfer, you see that MOF LUMO, that is MOF LUMO, it is giving this to ClO minus, and that is why that overall MOF emission is quenching and it is having fluorescence turn on and off response. On the other hand, this same scenario happens to ascorbic acid as well. But in presence of dual presence of MOF and ClO minus, you see that in addition of ascorbic acid to this enhances the electron intensity by 0.131 electron volt, and that is why the MOF is showing bright emission color. Okay, so this leads us to give the molecular tweezer effect. So this is the molecular level insight of ClO minus scavenging by ascorbic acid, where when we put the ClO minus, it is attracted by all the functionalities in the MOF. So we call it a tight state. It is binding energy, calculated binding energy from DST calculation is minus 19.2 kilocalorie per mole. So this is also called strong interaction and tight state. In presence of ascorbic acid, it is loosening. The ascorbic acid is scavenging this ClO minus towards itself or dragging it towards itself, and that is why it is loosening the interactions, and we call it a loose state. So in another way, this can be used for as a molecular tweezer, which is tweezing ClO minus in presence of this MOF and in ascorbic acid. So this is getting fluorescence off usual, and when in presence of ascorbic acid, the ascorbic acid drags the ClO minus towards itself and making the MOF free from the interaction, and that is why fluorescence is getting on. So that is how the fluorescence on is going in place. So this was one part of my talk, and the second part and last part of my talk is challenges on capture and conversion of carbon dioxide. As I told you that I also am working on these materials for sustainable catalysis and overall environmental remediation application. So apart from anti-counterfeiting and different pollutant monitoring, we are also working on CO2 absorption and utilization. And not only that, we are also working on different tandem catalysis for producing the important drug molecule, important pharmaceutically active molecule. So this is one of the slides that I'm showing, that conventional approaches for CO2 absorption. Why? What are the conventional approaches? First is aqueous alkaline amine, and second is porous adsorbents like activated carbon or zeolites. Now both have some disadvantage, because in case of aqueous alkyl amine, they are thermally unstable and corrosive in nature. They have high heat capacity, that is chemisorption in nature. They try to adhere to the CO2 and does not release it. So they have high energy input for regeneration as well because of this chemisorption. On the other hand, the porous adsorbents, conventional porous adsorbents, are having limited optimized pore, and they have poor tailorability, because as I told you that they cannot be tailored properly, and they have lower heat capacity. Because of that, the adsorption capacity is much less in nature. So in that sense, effective CO2 separation needs tailor-made adsorbent with molecule-specific interactions. And CO2, on the other hand, when we consider, they can be fruitfully used for different catalysis. For example, CO2 can be used for renewable fuels like alkanes, alkenes, alcohol, and acids. They can be also used for fine chemicals like olefins, urea, acids. They can be used for value-added chemicals like carbonates, cyclic carbonates, and carboxylates and carbamates. And they can be also used for synthetic fuels, methanol, dimethyl ether, formic acid, and methane. Now, the challenges regarding CO2 utilization are that this CO2 is in the highest oxidation state of carbon, so it is chemically inert, and that is why it demands backing of a catalyst. Now, various catalysts have been used like homogeneous, heterogeneous catalysis, but for homogeneous catalysts, they suffer from separation difficulties because you cannot separate after the reaction is done. On the other hand, most of the heterogeneous catalysts show inadequate activities. They need solvent for that, and they need also harsh reaction condition like very high temperature, like more than 150 degree centigrade temperature or more than 50 bar pressure even. So this is very high pressure that is not available, and that is why heterogeneous catalysis, most of them are not adequate. Now to this end, we have demonstrated the structural dynamism actuated reversible CO2 adsorption switch in a 3D covalent organic framework. So far, I have given the examples of metal organic framework where metal was one part of that. Now I am going to give you some of the glimpses of our research work in my lab that is having covalent organic framework. Now, 3D covalent framework is a unique category because mostly covalent bond framework is restricted for 2D sheets. That is more common. So this is an example of 2D covalent organic framework. On the other hand, this is an example of 3D covalent organic framework, which is three-dimensional in nature with extended framework through tetrahedral building block, and it is not that common. So we have targeted that challenge to use the 3D covalent organic framework. For that, we synthesize from this tetrahedral vertex and C2 linker. Using this, we form a diamondoid cage structure, which is having a 9-fold interpenetration overall. This is the side view, and we can see that this is a 3D framework with DIA topology. This is the top view, which shows the pores inside the framework. Now we have characterized this framework using diverse analytical tools. The first one is the CP-mass or 13C CP-mass NMR, PXRD verification, FTIR, and microporosity from bed surface area analysis, and also SAME and TAME authentication. And we also see that this framework is very selective to CO2. That is, CO2 adsorption is happening. What are the main features? Uptake capacity is higher than most of the 2D frameworks and many MOPs. So it is at 273 or 0 degree centigrade temperature, it is taking 88.35 centimeter cube per gram, and at 298, although it is little bit less because of higher temperature, room temperature, it is taking still 61.5 centimeter cube per gram. Now, the presence of accessible nitrogen donor sites from bipyridal link, as I showed you here, this is the bipyridal links. They actually help in this CO2 adsorption. So, the moderate QST, that isosteric heat of adsorption we get from Clausius-Clapeyron equation, which is a measure of adsorbent interaction, which shows that it is in the range of 35 kilojoule per mole, that is in physis option range. So this can be easily regenerated. That means that complete recurrence over multicyclic performance also we see that this can be easily regenerated. Now we see that it is highly selective towards CO2 than nitrogen. So this is very good in a sense that this COF can be used for flue gas separation or biogas separation in case of CO2 CH4 selectivity. Now we see a unique feature of this COF, that solvent assisted structural dynamism and switchable CO2 adsorption. So what happens? This is the normal or as made COF, which in presence of THF as a solvent, it goes from narrow pore to large pore. So we see that pores along this direction are of 8.97 into 18.21 angstrom square, which goes increased to 11.56 into 15.02 angstrom square. So that is in large pore system, and this is narrow pore system. So how this is happening? Because of reversible structural switching between activated and THF soak COF, we see that PXRD peak, you can see here that PXRD peak shifts, splits at 2 theta 5.8 degree, it splits and it shifts to lower 2 theta region that points a lattice expansion. Why it is happening? Because the CN pedal motion. Earlier I had shown that this COF is made up of this CN bond. So this CN bond can easily make a pedal motion, and because of that, it is having the imine bond is diverging more for such structural dynamism. Now pore stress structure converts back to the back in pristine COF upon solvent removal. Now the unique nature of this COF is that the THF soaked cough, that is lower pore cough, absorbs 21% higher CO2 than that of pristine cough, and lattice expansion causes more number of CO2 molecules over the entire stage pores. And THF excluded, when we exclude THF from the pore, it shows usual 85 centimeter cube per gram CO2 uptake, and that is why it is showing structural dynamism. So this is a kind of a sponge-like behavior where in presence of THF it is showing large pore, and in absence of THF it is showing narrow pore. So in presence of CO2 also this sponge-like behavior is there. So dynamic cough for switchable CO2 absorption. Now, second part of this work is synthesis and characterization of post-methylated ruthenium cough, because as I told you that it is having a bipyridal link. So externally, RuBPyCl2 is a homogeneous catalyst which can be grafted over the cough to make it heterogeneous. Now, homogeneous catalysis are having lot of problems stemming from their non-separable issues. So how to exclude that? So for that, we have heterogenize the homogeneous catalyst over the cough backbone, and we have characterized from several spectroanalytical measurements. I'm not going into the detail of that, but ultimately what we see that photosynthesis reaction, this is an important reaction in industry which I have performed, that is this synescen, and we see that broad absorption in visible region from UV visible DRS, so it is active as a photocatalyst. And we have also optimized that oxidative Stecker reaction. This is the Stecker reaction, and we see that in presence of RU cough, in presence of green solvent water, and in presence of atmospheric oxygen, that is having no other oxygen source, only from air, the reaction is working. So it is oxidative Stecker reaction is happening. So we have also shown the different subsets, and it is ultimately multiple cycle. It is recyclable up to 10 cycle. We have multiple fold benefit of this RU cough catalyst. First of all, it is homogeneous. RuBP2 is grafted over the cough as a recyclable catalyst. So you see that it is homogeneous, but it is recyclable because of heterogenization. Now, efficient C-alpha-H synescen is working at room temperature in water and in presence of aerobic oxygen under normal 18 watt UV lamp. Okay. So involvement of less toxic cyanide, that is organic cyanide, we have used, and subset scope is also broad. This important thing is that this is atom economic in a sense that iminium ion intermediate is in situ generated. As I told you that we are normally searching for more sustainable reaction. So atom economic or one-step reaction is more beneficial for that. So we have used that, and we can see that. Okay. So pore fitting induced size selectivity, whether this reaction is occurring inside the pore or not, how to understand that? So we saw that the larger sized substrates, they give much less conversion of the products, and this reaction occurred on the surface of the RU cough. That means that it is actually occurring on the pore. A different experiment was also done where we have done different type of activation. So this is usual activation. Without any activation, we see that huge decline in the formation of the yield of the product in the second cycle, and because the products are still occupying the voids of the pore, and that is why mostly surface reaction is occurring. On the other hand, when we use the same catalyst after proper washing or proper solvent, proper activation, the usual method is working. So it is actually working inside the pore, and this is the mechanistic path for visible light mediated oxidative synescen. I'm not going into detail, but the radical path was corroborated from the scavenging experiment by TEMPO. Okay, so in presence of TEMPO as a radical scavenger, it gives low yield, so it is going in a radical way pathway. So another example of this is one unique example of bifunctional anionic MOF with open copper 2 nodes for tandem CO2 fixation. So the research approach for that was that construction of robust framework with suitably oriented task-specific sites, probing the MOF for absorption and non-redox fixation of CO2, and transformation of CO2 to important product cyclic carbonate through tandem pathway. Now we have made this MOF using cobalt 2 as a metal. This ligand we have already shown, and this is a simple bipyridal ligand which shows this presence of this MOF. What are the saline features of this MOF is that it is having 3D framework with oxygen decorated pore, okay, allowing entrance of molecules with comparable molecular dimension. Now you can have that metal coordinated water molecules which can be easily cleaved upon activation to form a activated metal center which is more active towards certain reactions. Okay, now the nitrogen bridgehead of this can also act as a fluid basic environment and give that MOF for high CO2 absorption. So we have probed this MOF by different physicochemical stabilities, and we see that it is very, very stable in water, in boiling water, at pH 12, at pH 14. Also, it is stable in different solvents. We see a microporous nature from the bed surface area measurement, which is showing 503 meters square per gram. From thermal stability experiment from TGA, we see that it is very stable up to 400 degrees centigrade, and this is the XPS surface spectrum, which shows that all elements are present. This is the block shape morphology of the MOF, which does not change in harsh condition. For example, this is under acid condition, this is under harsh base condition, and this is under boiling water condition, which remains unaltered. So this MOF is very stable in nature. So for that, we made solvent-free CO2 cyclone addition. What it is the epoxide, which in presence of a catalyst can convert to cyclic carbonate. First, for that, we made a selection whether this MOF can have at all a CO2 absorption or not. Actually, the MOF can absorb CO2 and it is showing good amount of CO2 capture. With this is the isosteric heat of absorption, which is in the range of 30 to 35. And that means that it is in the physisorption range and not in the chemisorption range. So it can easily attract CO2 inside the pore. Okay. So with that we use this chemical reaction using this MOF as a catalyst, and in presence of styrene oxide 17.5 millimolar, in presence of this catalyst, very little amount of catalyst, in presence of TBAB, tetrabutyl ammonium bromide, as a co-catalyst in 60 degrees centigrade at 5 bar pressure, in 8 hours, we get complete conversion of the products. You see, in all the cases, it forms the products with high turnover number, and this is actually a benchmark in a sense, because normally CO2 gets activated at much higher temperature, more than 100 degrees centigrade, and much higher pressure, more than 10 bar. Here we are having much less amount of pressure and temperature. So this is multicyclic in nature. We can see that up to 5 cycles, there is no problem in the yield of cyclic carbonate, and we can also make the cycloaddition route. So first is the activation. So this is the active site, that is cobalt. It is getting activated. So after activation, it is interacting with the epoxide and followed by a bromonium and attack, ring closure, and followed by CO2 attack to form the ring closure product, and the catalyst is regenerated. Now, the most important part of that, normally this reaction has been done by several researchers. So there is no beauty or no, not a breakthrough one. But for breakthrough one, we made a tandem CO2 fixation with olefin, where we start this with styrene, and in presence of tetrabutyl hydrogen peroxide, it gets converted inside the MOF to epoxide, and this epoxide again reacts with CO2 to form a cyclic carbonate. So importance of this reaction is direct synthesis of cyclic carbonate without isolation of intermediate epoxide. So here we started with epoxide, and this epoxide is in situ generated here. So second is that concerted procedure reduces waste and time. So the essential prerequisite for that is that presence of redox switchable metal node within the MOF, and suitably sized pores for easy diffusion of substrate, and affinity of the framework towards CO2. Now, whether it is fulfilling or not, we have shown that styrene in presence of this catalyst, small amount of catalyst in TBAB and TBHP, it is actually showing good conversion. So we published this in Chemical Engineering Journal in 2022, and that is how this activation is occurring. First one is the radical pathway, wherein the epoxide is generated, and second one is the ionic pathway, where epoxide is getting activated and getting formed to cyclic carbonate in presence of this catalyst. So control experiment with tempo here again shows reduced 15% conversion. That means that it is going through a radical pathway in the initial state of this reaction, and cobalt 2 cobalt 3 transformation is, we can easily have evidence from LSB curve. So coming to finally to end my talk, this is my team in CSM Serai, and this is the picture of CSM Serai. Dr. Gaurav is at present postdoc at Uppsala University. Dr. Manpreet is a JSPS postdoc in Japan, and Dr. Ranadeep is having EPFL Switzerland as a postdoc, and Nilanjan is a postdoc in SMU Texas. Presently, Partho, Mahesh, Rudra, and Atoni is working with me. And finally, I would like to acknowledge the convener and organizing committee of Vigyan Yatra, CSR and DST HRB for financial support, and director Professor Kannan from CSM Sarai for his guidance and support, and centralized CF facility, of course, in CSM Sarai is very good, because of which we can publish the papers, and our active collaborators. And finally, thank you all for your kind attention.
Very nice talk, sir.
Thank you, sir.
It was really exciting to hear from you regarding the metal oxygen framework. It was really a wonderful talk. Yes, sir. Any questions, please, from audience?
Sudeep sir,
Yes, please.
you can stop your sharing.
Okay.
Yeah.
Is there any questions? Okay. Moving forward, now I invite my fellow researcher, Mr. Neogi Parmar, to deliver the vote of thanks.
Thank you, Tilak. Good evening, everyone. This is Mehul Parmar, research scholar from Department of Physics, Saurashtra University, Rajkot. It has been such an honor to be a part of this wonderful event. On behalf of the Department of Physics, Saurashtra University, Vigyan Gurjari, Gujarat Prant of Vigyan Bharati, VIBHA, GUJCOST, Department of Science and Technology, under Vigyan Gurjari Sammelan 2024. I would like to extend our heartfelt gratitude to each and every one of you for making this event very successful. First and foremost, I would like to express our deepest appreciation to our esteemed keynote speaker, Dr. VIBHA Kulshrestha and Dr. Subhadip Neogi sir. Your insights, research findings, and perspectives have enriched our understanding of the diverse facets of physics and have inspired fruitful discussion among the attendees. I would like to extend my heartfelt gratitude to our esteemed guest, Dr. Tejas Patalia sir. I would like to thank our chief patron, Professor Nilamari Ben Dave ma'am, Honorable Vice Chancellor of Saurashtra University, Rajkot, who provide us consistent support and encouragement for organizing such a wonderful event. I would like to thank our patrons and co-patrons, Professor Chaitanya Joshi sir, Professor Girish Bhimani sir, Professor Narottam Sahu sir, Professor R.G. Parmar sir. I would like to thank our conveners of Gujarat Vigyan Sammelan, Dr. Nikesh Shah sir and Dr. P.M. Joshi sir. I am very thankful to Dr. Mihir Joshi sir for chairing these sessions. Special word of thanks to event coordinators, Dr. Phy-SU sir and Dr. David sir for their tireless efforts in planning and executing every aspect of this event flawlessly. Their dedication and commitment have been invaluable in ensuring a smooth and enriching experience for all participants. Last but not least, a special thanks goes to PhD research scholar and volunteer Mr. Chintan Panchasra for technical assistance support throughout the Vigyan Yatra. We would like to thank all the attendees for their active participation, insightful questions, and contribution to making this Vigyan Yatra a truly memorable and rewarding experience. We also thanks to member of press and media for the wider publicity and outreach. Thank you.
Thank you.
Now, at the end of this 9-day series of conferences, I would like to invite Professor Nikesh Shah, Head of the Department and Convener of Gujarat Vigyan Sammelan 2024, to present the concluding remarks and address the gathering. Over to you, sir.
Thank you, Tilak. First of all, today's speaker, Dr. Vaibhavji, and Dr. Subdipji, thank you very much for providing a very nice talk. Today's chairperson, our head of department, Professor Mihir Bhai Joshi sir, my colleagues, Dr. Piyush, Dr. David, and all coordinators, all participants. I would like to say first thank to our Vice Chancellor, Professor Nilambari Ben Dave, to supporting us and promoting us to organize this Vigyan Yatra, a series of conferences. I am also thankful our Gujarat Prant President, Professor Chaitanya Joshi ji, our Faculty Dean, Professor Girish Bhai Bhimani, and the support from GUJCOST Gandhinagar, Dr. Narottam Sahu sir, and all participants, all speakers. That is, we started on 4th March with Dr. Vishal, that is what, from energetic space science to last today, that we have the two speaker from Bhavnagar. Whatever that, in case of when we announced this Vigyan Yatra, more than 900 participants, that most of that 30% are scientists and faculties and research students, UG students, PG students throughout the India, each and every state of India. But what we observed, that as a registration, it was 900 plus, but on first day, 4th March, that around 300 participants joined this Vigyan Yatra. Then day by day, whatever we observe in case of that online system, that there is decreasing order. That is what, from 300 to today, I think presently 68. Earlier it was when talk was running that more than 70 participants was there. But what interesting thing that I observed every day, I was observing the participants' behavior, that who are present, they are throughout the country. It is not like only Gujarat or only Maharashtra. That is one thing. Second important thing, that in case of that, that all are that invited speakers are very prominent. They talk very beautifully, interesting, and due to that, that starting of 2:30, when these participants join, and the completion of this 5:30, most of our remain present. That is what the that is the attraction or magnetization of the speaker that who delivered the talk. So I am thankful to all speakers. I am also thankful to all participants, and I am also thankful to all team members because they took a lot of pain to make this Vigyan Yatra success. All the best, and I am requesting all of you who are present, who are not present, connected in WhatsApp group. So in future we will organize again the new kind of series. Thank you very much. Thank you.
Thank you, everyone.